Example number 2. Identify the values of the variables for which each radical is defined and then simplify. So this is kind of taking what we did in the last lesson where a radical is defined and then solving. Okay, we did evaluating or simplifying. We did simplify a little bit, but we only were dealing with one radical. Now we're dealing with multiple radicals. So first things first, step 1, we need to state we're defined. So we know that the radicand, since it's a square root, a radicand can, oh, that reminds me of something from, is it Charlie and the Chocolate Factory? I don't know, you guys get back to me on that. Anyways, a radicand cannot be negative, so that means that a must be greater than or equal to 0. Done. That's all we can do. So now they're all like terms because it's 6 of this quantity root a plus 5 of this quantity root a minus 11 of this quantity root a. So 6 plus 5 is 11 minus 11 is just going to be 0 root a's. So I'm just going to put 0. Whew! All right. That's not so bad. All right. So with b, this is a little bit more tricky when we have 2 variables here. So first things first, step 1 is defining and then step 2 is simplifying. Okay, we're going to define it. So we're saying that a squared times b must be greater than or equal to 0 because we're dealing with a square root again. Well, here's the thing. A squared is always going to be positive because a squared will always contribute positive even if a is greater than 0 is less than 0. So here I can say a can be anything. A can be any value because no matter what value I put in here, since it's squared, it's going to create this to be positive. So if I were to look at this, then I know that b must be greater than or equal to 0. So there are 2 pieces of this. A can be anything, because if I put anything in for this a, and I square it, it's going to contribute positively to this. Okay, it's going to create a positive value for this. The only thing that could mess it up by making it negative is if this b is less than 0. So in that way, b always has to be greater than 0. Okay, well, now let's do step 2, which is simplifying. So I'm noticing that we have perfect square factors in here, so I'm going to simplify that. So I'm going to say, okay, 50 here is 25 times 2 times a squared, which is a perfect square factor here, times b, minus the square root of 8 times 2 times a squared times b. All right, so we have something that's common here. We have 2 and a b, and we have 2 and a b. Oh, sorry, not 8 times 2. My bad, that should be 4. 4 times 2. So 8 times 2 would be 16. Oh, no, that's confusing. So I'm going to pull out what is a perfect square factor. So I'm just going to say, okay, 25a squared. I'm just going to take it in 2 steps here because it's a little bit difficult. So we have the 25 taken care of and the a squared taken care of. So what we're left with is 2b minus 4a squared. Got the 4 and the a squared, and what's left over is 2b. So we have like terms here. That's great. So let's figure out what we can do with this coefficient. So we're saying, okay, 25, so the square root of 25 is 5. The square root of a squared is the absolute value of a times 2 root of 2b minus 2 times the absolute value of a times root 2b. Now we said that a could be anything. Because we said that a could be anything, we must ensure that we have the principal square root thing happening here. So we would get the positive value for that. So in this case, it's very important. Now say if I said a has to be greater than or equal to 0, then we wouldn't need the absolute value because it could only be positive. But since we said that a could be any value, both positive and negative, we have to have it in the absolute values here. So we have 5 of this quantity, and we subtract 2 of this quantity. It's going to be 3 absolute value of a times 2b, or the root of 2b. Last but not least, first things first, let's define where these are true. Now, we can do a little bit of a happy math dance party because we have an odd index. Woohoo! It means it's a free-for-all. It means that like the variables can be anything. So I can say p and q are element of reals, and we don't have to think about it anything other than that, because you can have negative values underneath a radical that has an odd index. Like I can say, okay, the cubed root of -8, oh yeah, no problem, that's -2. It's not a problem. Whereas if I was to say, okay, I need the square root of -16, you're like, can't do it. There's an error. Okay? So done and done. We've defined where it is. Defined for where it can happen. So I'm going to look at this and thank you, mathematical gods, because the cubed root of 27 is very simply put. It's just 3. I can simplify it right here, right now. There are no factors to contend with. So I'm going to say, okay, so this is going to be 3. The third root of p to the 3 is simply going to be p, and we're left with the cubed root of q plus 8. The cubed root of p cubed is simply p. Don't have to worry about absolute value bars because it's an odd index, and then what I'm left with is the cubed root of q. So I have 3 of these quantities, and I want to add 8 of these quantities to them, so then I have 11p times the cubed root of q. Done.